After watching this video lecture, students are going to be able to calculate gas law problems using Graham's law. Graham's law is going to apply to the diffusion and effusion of gases. Basically, diffusion is the mixing of gases and the even distribution of those gas molecules in the mixture. Okay, this is what we take advantage of, and the fact that our air is a mixture of nitrogen and oxygen and several other gases. But because diffusion happens and the gases spread evenly and consistently through the container, we're able to breathe easily in every part of the room. Okay, effusion is the escaping of a gas through small openings. So think of like a puncture in your tire or something of that sort. So some considerations to think about when looking at Graham's law problems. Basically, our kinetic energy of our particles, of our gaseous molecules, is going to be determined by the temperature of the gas. Okay, and so particles at the same temperature with the same kinetic energy are going to have different speeds based on their mass. So heavier molecules are going to move more slowly, and lighter molecules are going to move more rapidly. So what we have here is the basic form of Graham's law. We have the relationship between the velocities or speeds or rates of two different gases being equal to the square root of their masses, okay, as you see here. Now, a couple of things I want to point out. First of all, please notice that the speed or velocity or rate of movement of A in the equation is going to be basically across and down from the mass of that particular gas. Okay, so when you're doing these problems, please make sure that your rates and the masses of that corresponding gas are basically kitty corner to each other. So we're going to go ahead and apply some of these problems here. All right, so if we go ahead and we look at this problem, it says determine the relative rate of diffusion for krypton and bromine. Okay, so in this problem, right, we're going to have our gases, rates, okay, and then we're going to have their masses. Okay, now typically what I like to do is I like to have my lighter gas on top in my problems. This just leads to values that I feel like are more logical in terms of explanation, and we'll talk about that here in a second when we look at our calculation answer. Okay, so we have our gas molecules corresponding to bromine and krypton, okay, and we want their relative rates. So we're solving for the relationship between these two rates. Okay, and so what we're going to do is we're going to plug in our molar masses for each of these gases, okay, and that's going to equal basically 159.808, okay, divided by, let's see, krypton is 84.80, okay, and that's going to give us the relationship between krypton's rate and bromine's rate. Okay, so we're going to go ahead and plug this in our calculator. That's going to give us 1.37, okay. And so what this tells us, this number here tells us, is that the rate of movement of krypton is 1.37 times faster than the rate of movement of bromine. Okay, now this could have totally been done the other way, and we're going to go ahead and look at that real quick. And as we can see from our calculation here, we get a different answer, and that's because we are relating them differently. Okay, so basically, the rate of movement of bromine gas is going to be 0.728 times as fast as the rate of krypton. So in my head, this just makes more sense. Being able to say one thing is faster than the other is easier to comprehend for me personally, but this answer too would have been correct. All right, we're going to go ahead and look at another problem here. It says an unknown gas diffuses 4.0 times faster than O2. Find its molar mass. Okay, so we've been told here a relative relationship between our O2 and our unknown gas. So our unknown gas is 4 times faster than our O2. Okay, so if we go ahead and we look at our setup here, okay, we are going to need to be solving for the mass of our unknown. I personally like to have the mass of my unknown set up on top. It just simplifies calculations, in my opinion. Okay, but you can do the manipulations as you see fit. Okay, so we're going to have O2 here, we're going to have O2 here, and we're going to have our unknown gas there. Okay, now you may be like, well, what information do I know here? Okay, well, I know that the rate of diffusion of the unknown is 4 times the rate of diffusion of my O2. Okay, so that relationship here, it doesn't really matter what the values are. It just matters that the rate of movement of my unknown gas is 4 times that of my known gas. Okay, so I'm just going to plug 1 and 4 in to these 2 portions of the equation. Okay, I also know the mass of my oxygen. Okay, so 31.998. Okay, and then that's going to allow me to go ahead and manipulate and solve for the mass of my unknown. Okay, now the biggest mistake that people make here is they forget to square both sides. Okay, we need to get rid of the square root here so we can isolate. And that's going to give us 0.0625 is equal to the mass of question mark 998. Okay, and the mass question mark, or the unknown gas, is going to be multiplied by the 0.0625. Okay, and that's going to give us a mass of our unknown of 1.99 grams per mole. Okay, and if we look at this, right, the mass of our unknown gas is significantly less than the mass of our known gas. And it makes sense that it would be significantly faster in terms of its movement at the same temperature. Okay, now some of you may be wondering about significant figures and all that. I'm not really concerned about it in the context of Graham's law problems. It's mostly just a relational problem set that I'm looking at for you to be able to calculate.